The Cold War produced machines whose scale, complexity, and purpose often bordered on the unreal. Driven by fear, secrecy, and the logic of total deterrence, both superpowers built systems designed not for battlefield efficiency, but for psychological dominance, survivability, and absolute escalation control. Many of these projects were so specialized, expensive, or politically inconvenient that they were quietly retired, canceled, or forgotten once their strategic moment passed. Others survived in obscurity, overshadowed by more famous weapons despite their enormous influence on military and technological history. Examining these machines reveals how far nations were willing to push engineering, infrastructure, and risk in preparation for conflicts that, mercifully, never came. The BZHRK Molodets, a nuclear missile train disguised as a freight line. The BZHRK Molodets was one of the most unconventional and psychologically intimidating nuclear weapon systems ever deployed by the Soviet Union. The designation stood for Boyevoy Железнодорожный Raketny Complex, translated as Combat Railway Missile Complex. The idea emerged during the late 1970s, when Soviet planners became increasingly concerned about the vulnerability of fixed missile silos to American reconnaissance satellites and improving precision strike capabilities. Responsibility for development was assigned to the Yuzhnoye Design Bureau, led by Chief Designer Vladimir Utkin, with additional work distributed across multiple Soviet defense ministries. After years of testing and refinement, the first complete Molodet systems officially entered operational service in 1987. At its core, Molodets relied on deception and mobility. Each operational unit consisted of a train deliberately disguised as an ordinary refrigerated freight convoy. Concealed inside were 3 RT-23 UTTKH solid-fuel intercontinental ballistic missiles, known to NATO as the SS-24 Scalpel. Each missile weighed more than 100 metric tons and was capable of carrying up to 10 independently targetable nuclear warheads. Despite these extreme specifications, the launch cars were engineered to conform to civilian railcar dimensions, axle loads, and braking profiles, allowing them to move freely across standard rail lines without immediate detection. The strategic value of Molodets lay in its survivability. The Soviet Union operated more than 100,000 kilometers of railway, creating an immense and unpredictable operating environment for any adversary attempting to track the trains. Launches could be conducted from pre-selected reinforced sections of track, using a cold launch system that expelled the missile vertically before engine ignition. Early trials reportedly unsettled engineers, as the forces involved pushed rails, suspension assemblies, and hydraulic launch mechanisms close to their structural limits. Each BZHRK train carried a crew of approximately 70 personnel who lived entirely on board during extended patrols lasting weeks. The full consist included command cars, diesel power units, fuel tankers, security cars, and launch cars, all painted and marked to resemble civilian rolling stock. Even experienced Western intelligence analysts struggled to reliably distinguish Molodets trains from normal freight traffic using satellite imagery alone. The system remained operational from 1987 to 2005, surviving the collapse of the Soviet Union and continuing briefly under Russian control. Its retirement was driven by arms reduction agreements, particularly START II, as well as rising maintenance costs and aging infrastructure. By 2007, all launch cars had been dismantled, ending one of the Cold War's most audacious mobile deterrent concepts. Project 941, Akula, Typhoon class, the largest submarine ever built, now largely abandoned. Project 941. Akula, known in NATO designation as the Typhoon class, represented the absolute peak of Soviet Cold War submarine engineering and strategic ambition. Conceived during the early 1970s, the project was intended to counter the growing effectiveness of American anti-submarine warfare and to provide the Soviet Union with a virtually invulnerable, sea-based nuclear deterrent. Design responsibility was assigned to the Rubin Central Design Bureau under Chief Designer Sergei Kovalev, while construction was carried out at the Sevmash shipyard in Severodvinsk. The lead submarine, TK-208 Dmitry Donskoy, was laid down in 1976 and formally entered service in 1981. What made Project 941 unprecedented was its sheer scale and unconventional internal layout. At over 170 meters in length, and with a submerged displacement exceeding 48,000 tons, Typhoon-class submarines remain the largest ever built. Rather than a single pressure hull, the design used multiple parallel titanium hulls housed within a massive outer casing. This arrangement improved survivability and allowed extensive internal volume for crew habitability, weapons storage, and redundancy. The submarines were powered by two OK-650 pressurized water nuclear reactors, giving them effectively unlimited range and prolonged patrol endurance. The primary mission of Project 941 was strategic nuclear deterrence. Each submarine carried 20 R-39 RIF solid-fuel submarine-launched ballistic missiles, designated SSN-20 Sturgeon by NATO. Each missile was capable of carrying 10 MIRV nuclear warheads, giving a single Typhoon the theoretical ability to strike 200 targets. To support Arctic bastion operations, the hull was reinforced for under-ice navigation, and the sail was strengthened to break through ice up to 2 meters thick during missile launch operations. Despite their power, Typhoon-class submarines were extremely expensive to operate and maintain. Following the collapse of the Soviet Union in 1991, funding shortages and arms reduction treaties sharply reduced their relevance. START-Y and subsequent agreements limited strategic missile deployments, while the aging R-39 missile system became increasingly impractical to sustain. By 1996, most Typhoon submarines had been placed in reserve. By 2013, only TK-208 Dmitry Donskoy remained active, repurposed as a test platform for the Bulava missile program. The remaining hulls were gradually decommissioned and scrapped, marking the end of the most imposing submarines ever to patrol the world's oceans. Although often mythologized in popular media, their true significance lay not in secrecy, but in scale, endurance, and the strategic psychology of assured retaliation, making Project 941 a symbol of late Soviet industrial capacity and Cold War excess. The AN-225 Mriya, a flying artifact of Soviet strategic overkill. The Antonov AN-225 Mriya was the largest and heaviest airplane ever to achieve sustained flight, a product of late Cold War priorities that valued brute capacity over economic efficiency. Its origins trace back to the early 1980s, when the Soviet Union required an aircraft capable of transporting the Buran space shuttle and oversized Energia rocket components across vast internal distances. The task was assigned to the Antonov Design Bureau in Kiev, led by Chief Designer Viktor Tolmachev, building upon experience gained from the smaller, but still massive, AN-124 Ruslan. Formal development began in 1984, with the first airframe completed at the Antonov serial production plant. The AN-225 first flew on 21 December 1988, immediately redefining the upper limits of aerospace engineering. With a maximum takeoff weight of approximately 640 metric tons, the aircraft dwarfed every existing transport platform. It was powered by 6 Ivchenko Progress D-18T turbofan engines, each producing over 229 kilonewtons of thrust. The wingspan measured 88.4 meters, requiring a reinforced multi-wheel landing gear system consisting of 32 wheels to distribute weight across runways. Every structural element was scaled upward, including the reinforced fuselage spine designed to carry the Buran orbiter externally. Unlike Western heavy lifters, the AN-225 was built for a highly specific mission rather than flexible logistics. Internally, its cargo bay could accommodate loads exceeding 250 metric tons, enabling transport of equipment that no other aircraft could move in one piece. During testing and early operations, Mriya set more than 200 world aviation records for payload weight, altitude, and combined performance categories, many of which remain unbroken. The collapse of the Soviet Union in 1991 abruptly ended the strategic rationale for the aircraft. With the cancellation of the Buran program in 1993, the AN-225 lost its primary mission. A second partially completed airframe was abandoned, and the sole operational aircraft was placed in storage for several years. It returned to service in 2001 after modernization, operating as a commercial heavy transport for Antonov Airlines and carrying generators, locomotives, and humanitarian aid worldwide. Despite its later civilian role, the AN-225 remained a relic of Cold War industrial philosophy, where prestige projects justified extraordinary expense. Its story ended tragically in February 2022, when the aircraft was destroyed during fighting at Hostomel Airport during the Russian invasion of Ukraine. Although plans for reconstruction were discussed, Mriya ultimately became a symbol of a vanished era, representing both the technical brilliance and unsustainable excess of Soviet strategic engineering. Zveno-SPB, a parasite bomber system, too large and too strange to last. The Zveno-SPB program was one of the most unconventional aerial combat concepts ever fielded, emerging from interwar Soviet experimentation with composite aircraft. The idea was developed during the early 1930s under the leadership of aviation engineer Vladimir Vakhmistrov, who sought to overcome the limited range and payload of contemporary fighter aircraft. His solution was Zveno, meaning link, a system in which small fighters were physically attached to a larger bomber and released near the target. The most operationally successful variant was the Zveno-SPB, with SPB standing for Sostavnoy Pikiruyushchi Bombardirovshchik, or Combined Dive Bomber. The system paired the aging Tupolev TB-34 engine-heavy bomber with two Polikarpov R-16 fighters mounted beneath its wings. The TB-3 served as a flying launch platform, carrying the fighters to combat range while conserving their fuel and extending their effective radius. Once released, the I-16S acted as precision dive bombers, each carrying two 250-kilogram bombs, a payload that would otherwise have severely restricted their range and maneuverability if launched independently. Development and testing of Zveno configurations took place throughout the 1930s, with multiple arrangements evaluated, including fighters mounted above the wings and even beneath the fuselage. The Zveno-SPB configuration was finalized shortly before the outbreak of the Second World War, representing the only version to see genuine combat use. Operational deployment occurred in 1941, during the opening phase of the German invasion of the Soviet Union. Zveno-SPB units conducted a small number of combat missions against Romanian targets, most notably the King Carol I Bridge over the Danube near Cernavoda. Flying from bases in Crimea, TB-3 motherships carried their parasite fighters close to the target area before releasing them for steep dive bombing attacks. These missions achieved tactical success, damaging strategic infrastructure beyond the reach of conventional Soviet light bombers at the time. Importantly, the system proved that the concept was technically viable under real combat conditions. Despite this success, Zveno-SPB was ultimately a dead end. The TB-3 was already obsolete by 1941, slow, lightly defended, and highly vulnerable to modern fighters. The complexity of operations, combined with rapid advances in long-range bombers and improved fighter performance, rendered the composite aircraft concept unnecessary. By late 1941, Zveno units were disbanded. Zveno-SPB remains a historical curiosity, not because it failed outright, but because it briefly worked in an era when aviation doctrine had not yet settled. It stands as a reminder of how far Soviet engineers were willing to push unconventional solutions in the search for strategic advantage. The B-36 Peacemaker, a nuclear bomber. So massive, it flew before jets were ready. The Convair B-36 Peacemaker was the largest mass-produced piston-powered bomber ever built and one of the most ambitious aircraft projects in United States military history. Its origins dated back to 1941, when the U.S. Army Air Forces feared that Britain might fall to Nazi Germany, leaving North America isolated from forward air bases. In response, a requirement was issued for a bomber capable of striking targets in Europe directly from the continental United States. Consolidated Aircraft, later Convair, was awarded the contract, and early design work began under the leadership of engineer Isaac Macklin. Development was prolonged by wartime production priorities and technical complexity. The first prototype, designated XB-36, made its maiden flight on the 8th of August 1946, after the Second World War had already ended. By the time it entered service in 1948, the B-36 had transitioned from a conventional bomber concept into a cornerstone of early Cold War nuclear deterrence. Its immense size was driven by the need for extreme range, with an unrefueled combat radius exceeding 6,400 kilometers. The B-36 was powered by 6 Pratt & Whitney R-4360 Wasp major radial piston engines mounted in a pusher configuration, giving rise to the famous description 6 turning and 4 burning. After later variants added 4 General Electric J, 4 7 turbojet engines for increased speed during takeoff and combat dash. The wingspan measured 70.1 meters, larger than many modern airliners, and the aircraft's maximum takeoff weight exceeded 185 metric tons. At the time of its introduction, no existing jet bomber could match its payload or range. Strategically, the Peacemaker served as the primary delivery platform for the first generation of American nuclear weapons. Early atomic bombs were extremely large and heavy, and only the B-36 could reliably carry them intercontinental distances. Defensive armament was extensive, consisting of remotely controlled gun turrets armed with 20mm cannons, though these systems became increasingly obsolete as jet interceptors improved. The aircraft was controversial throughout its service life. Critics argued it was vulnerable, expensive, and outdated, while proponents within the Strategic Air Command viewed it as an essential stopgap until true long-range jet bombers became viable. Political debates in 1949 over its funding highlighted tensions between the U.S. Air Force and Navy regarding nuclear delivery doctrine. The B-36 remained in frontline service from 1948 to 1959, when it was finally replaced by the jet-powered B-52 Stratofortress. Although it never dropped a weapon in combat, the Peacemaker played a critical deterrent role during the early Cold War, bridging the technological gap between propeller-driven bombers and the jet age. Project 1160 Orel, the Soviet supercarrier that never sailed. Project 1160 Orel was the Soviet Union's most ambitious attempt to build a true nuclear-powered aircraft carrier comparable to the American Nimitz class. The concept emerged during the late 1960s, when Soviet naval leadership began reassessing its long-standing rejection of carrier strike doctrine. Admiral Sergei Gorshkov, Commander-in-Chief of the Soviet Navy, was the primary advocate behind the project, arguing that global naval power required fixed-wing aviation capable of operating far from land-based airfields. Formal design work began around 1969, with responsibility assigned to the Nevskoye Design Bureau in Leningrad. Unlike earlier Soviet aviation ships, Project 1160 was envisioned as a full fleet carrier, rather than a missile cruiser with limited air capability. Early design studies called for a displacement of approximately 80,000 to 85,000 tons, placing it firmly in the supercarrier category. The ship was to be powered by nuclear reactors, granting it extended endurance and operational reach similar to American carriers. Planned dimensions included a flight deck long enough to support catapult-assisted takeoffs, a critical departure from Soviet reliance on short takeoff aircraft. The air wing was another radical shift. Project 1160 was designed to operate conventional fixed-wing fighters and strike aircraft. including navalized variants of the MiG-23 and Su-24, as well as early concepts that later influenced the Su-33. Steam catapults were incorporated into the design, marking the first serious Soviet attempt to master this complex technology. Defensive systems were to include layered surface-to-air missiles and close-in weapons, reflecting Soviet emphasis on ship survivability in contested environments. Despite its promise, Project 1160 faced insurmountable political and industrial obstacles. The Soviet defense establishment was divided, with the strategic rocket forces and submarine advocates opposing the diversion of resources to carriers. Nuclear propulsion further increased costs and complexity, while catapult development lagged behind schedule. By the mid-1970s, economic pressures and shifting priorities forced repeated downsizing of the design. In 1976, Project 1160 was formally canceled before construction could begin. Its conceptual lineage, however, did not disappear. Lessons from Orel directly influenced later projects, including Project 1153 and ultimately Project 114 3.5, which produced Admiral Kuznetsov. These successors abandoned catapults and nuclear propulsion, reflecting compromise rather than original intent. Project 1160 remains significant precisely because it never sailed. It represents the moment when the Soviet Navy came closest to matching American carrier power symmetrically, before economic reality and institutional resistance curtailed the ambition. Its cancellation marked the end of any Soviet pursuit of true supercarriers during the Cold War. The R-7 Semyorka launch complex, a rocket so big it still shapes spaceflight today. The R-7 Semyorka was the world's first intercontinental ballistic missile and the foundation upon which Soviet and later Russian spaceflight was built. Its development began in 1953 under the leadership of chief designer Sergei Korolev at OKB-1, following a directive from the Soviet government to create a missile capable of delivering a nuclear warhead across intercontinental distances. At the time, Soviet nuclear weapons were extremely heavy, forcing engineers to design a launch vehicle of unprecedented size and power. The result was not only a weapon system, but a launch architecture that continues to influence orbital spaceflight today. Unlike later missiles, the R-7 used a distinctive clustered design. It consisted of a central core stage surrounded by 4 strap-on boosters, all ignited simultaneously at liftoff. This configuration solved thrust limitations while maintaining structural integrity, but it also made the missile impractical as a rapid response weapon. The R-7 required hours of preparation, cryogenic liquid oxygen fueling, and a fixed launch site. To support it, entirely new ground infrastructure had to be constructed, leading to the creation of the Baikonur Cosmodrome in Kazakhstan. The first successful test flight of the R-7 occurred on 21 August 1957, demonstrating that the Soviet Union possessed a functional ICBM. Only weeks later, on 4 October 1957, a modified R-7 launched Sputnik 1, the world's first artificial satellite. This event transformed the missile into a space launcher and ignited the space race. Subsequent variants of the R-7 family launched Sputnik 2, Vostok 1 carrying Yuri Gagarin in 1961, and later Voskhod and Soyuz missions. Militarily, the R-7 was short-lived. It entered limited operational service in 1960 but was quickly supplanted by storable propellant missiles that could be kept fueled and launched rapidly. However, its launch complex proved ideal for space operations. The pad design featured a unique tulip support system, where the rocket was held upright by arms that opened outward at liftoff, a concept still used today. This approach reduced structural stress and simplified ground handling for very large rockets. The true legacy of the R-7 lies in its evolutionary continuity. The Soyuz launch vehicle, still flying in the present day, is a direct descendant of the original Semyorka. While engines, avionics, and safety systems have been modernized, the fundamental layout remains recognizable. No other launch system in history has demonstrated such longevity. The R-7 Semyorka launch complex endures because it was overbuilt for its original purpose. Designed to deliver the heaviest weapons of its era, it instead became the backbone of human spaceflight, shaping orbital access for more than 6 decades. Project 705 Mriya, Alpha class, a titanium submarine that terrified NATO sonar operators. Project 705 Mriya, known to NATO as the Alpha class, was one of the most radical submarine designs ever to enter operational service. Conceived in the late 1950s and early 1960s, the project aimed to create an interceptor submarine capable of hunting and destroying enemy ballistic missile submarines before they could launch. Design responsibility was shared primarily between the Malekith Design Bureau and SKB 143 under the leadership of chief designer Mikhail Rusanov, with later contributions by Georgy Chernyshev. From the outset, speed, depth, and automation were prioritized above all other considerations. The defining feature of Project 705 was its titanium alloy pressure hull. Unlike conventional steel, titanium offered exceptional strength, corrosion resistance, and reduced magnetic signature, allowing the submarine to dive deeper and maneuver more aggressively. This choice, however, imposed enormous industrial challenges, requiring specialized welding techniques and driving costs to extreme levels. The resulting hull enabled operating depths estimated to exceed 600 meters, far beyond most NATO attack submarines of the era. Equally unconventional was the propulsion system. Mriya submarines were powered by a compact liquid metal-cooled nuclear reactor using a lead-bismuth eutectic coolant. This reactor design allowed extremely high power output for its size, enabling submerged speeds reportedly exceeding 40 knots. Such performance made the Alpha class the fastest nuclear submarines ever built, capable of outrunning torpedoes and rapidly repositioning in combat scenarios. NATO sonar operators found them particularly alarming, as their speed and acceleration challenged existing tracking doctrines. Automation was another revolutionary aspect. Project 705 was designed to operate with a crew of approximately 32 men, less than half that of comparable Western submarines. Advanced control systems centralized propulsion, navigation, and weapons management, reducing manpower requirements but increasing technical complexity. Living conditions were austere, reflecting the assumption that missions would be short and intensely focused on interception rather than prolonged patrol. The first Alpha-class submarine entered service in 1977, with a total of 7 units commissioned between 1977 to 1981. Despite impressive performance, operational realities quickly revealed serious drawbacks. The liquid metal reactor required constant heating to prevent coolant solidification, making maintenance difficult and unforgiving. Shore infrastructure was inadequate, and reactor incidents further undermined confidence in the design. Costs were also unsustainable, particularly as quieter and more balanced attack submarines entered service. By the late 1980s, Project 705 was effectively sidelined, and the last units were decommissioned by 1996. Although the program was short-lived, its impact was disproportionate to its numbers. Mriya demonstrated what was technologically possible when performance was pushed to extremes, and it forced NATO planners to reconsider assumptions about submarine speed, depth, and interception capability. It remains one of the most intimidating and impractical submarines of the Cold War. The Duga radar array, a steel wall that knocked on the world's radios. The Duga radar array was one of the most enigmatic and intrusive electronic systems of the Cold War, known to radio operators worldwide as the Russian woodpecker. Developed by the Soviet Union as part of its ballistic missile early warning network, Duga was an over-the-horizon radar designed to detect intercontinental ballistic missile launches from thousands of kilometers away. Development began in the late 1960s under the direction of the Soviet Ministry of Radio Industry, with scientific oversight from the Institute of Radio Engineering and Electronics. The primary operational installation was constructed near Chernobyl in the Ukrainian SSR, with a secondary site near Komsomolsk on Amur in the Russian Far East. Unlike conventional radar, Duga relied on high-frequency radio waves bounced off the ionosphere to detect objects beyond the curvature of the Earth. This required immense transmitting power and antenna structures of unprecedented scale. The Chernobyl Duga array consisted of two massive steel walls of antennas, one approximately 150 meters tall and the other about 90 meters tall, stretching nearly 700 meters in length. Supporting infrastructure included dedicated power facilities, signal processing buildings, and the closed military town of Chernobyl II, which did not appear on civilian maps. Duga became operational around 1976, when its distinctive pulsed signal began interfering with shortwave radio broadcasts worldwide. The rapid, repetitive tapping sound earned it the nickname Woodpecker, and it disrupted aviation, maritime communications, amateur radio, and international broadcasting. Despite numerous diplomatic complaints, the Soviet Union initially denied responsibility. Western analysts eventually identified the source and purpose through signal analysis and satellite imagery, confirming its role in missile detection rather than communications jamming. In theory, Duga could provide early warning of missile launches from the continental United States by detecting the ionospheric disturbances created by rising rockets. In practice, the system suffered from reliability issues, false positives, and vulnerability to changing ionospheric conditions. Advances in satellite-based infrared early warning systems further reduced its strategic value during the late Cold War. The 1986 Chernobyl nuclear disaster had a direct impact on the radar complex. Although the Duga array itself was not destroyed, the evacuation of the surrounding exclusion zone severely disrupted operations. By 1989, the system was shut down entirely as the Soviet Union shifted resources toward space-based warning platforms. Following the dissolution of the USSR in 1991, the site was abandoned. Today, the rusting Duga antennas still stand as one of the most striking Cold War relics ever built. More than a weapon, Duga was an experiment at the outer edge of physics, scale, and ambition. Its legacy lives on not through success, but through the global disruption it caused, and the reminder that Cold War defense systems often affected the entire planet, not just their intended adversaries. The Mi-12 Homer, the largest helicopter ever to leave the ground. The Mi-12, designated V-12 during development and known to NATO as Homer, remains the largest helicopter ever to fly. It was conceived in the late 1950s as a response to a specific strategic requirement of the Soviet military: the ability to transport extremely heavy ballistic missile components to remote deployment sites with little or no road or rail infrastructure. The project was assigned to the Mill Design Bureau, led by Chief Designer Mikhail Mill, whose office already had extensive experience with heavy rotary wing aircraft. Formal development began in 1959, but the Mi-12 was not simply an enlarged version of existing helicopters. Engineers quickly realized that a conventional single-rotor layout was impractical at the required scale. Instead, they adopted a transverse twin-rotor configuration, mounting two massive rotor systems on wing-like structures extending from either side of the fuselage. Each rotor was derived from the Mi-6, then the world's largest operational helicopter, and powered by a pair of Soloviev D-25 VF turboshaft engines, giving the Mi-12 a total of 4 engines. The aircraft's size was unprecedented. It had a maximum takeoff weight exceeding 105 metric tons and a cargo hold large enough to accommodate trucks, artillery, or missile sections internally. The fuselage featured a rear loading ramp similar to fixed-wing transports, reflecting its logistical rather than tactical mission. The first prototype flew on July 10, 1968, immediately demonstrating that the concept was viable, despite widespread skepticism within the aviation community. The Mi-12's most famous achievement occurred in 1969, when it lifted a payload of 44,205 kilograms to an altitude of 2,255 meters, setting an absolute world record for helicopters that still stands. These flights proved that rotary wing aircraft could operate at weights previously thought impossible. Performance was stable, and test pilots reported surprisingly predictable handling given the aircraft's enormous mass. Despite its success, the Mi-12 never entered production. By the early 1970s, the strategic context that justified its creation had changed. Soviet missile forces shifted toward mobile launchers and silo-based systems that no longer required air transport of oversized components. At the same time, heavy fixed-wing transports such as the AN-22 and later the AN-124 offered more efficient solutions for strategic lift. The Mi-12 was also complex, expensive, and limited in speed and range compared to airplanes. Only 2 prototypes were completed, and the program was officially canceled in the early 1970s. One airframe was preserved and placed on display, while the other was used for ground testing. The Mi-12 Homer remains a singular achievement in aviation history, representing the absolute upper boundary of helicopter design. It was not a technological failure, but rather a solution to a problem that ceased to exist, leaving behind a record that has never been surpassed. Project 667 BDRM Delta IV, the silent giants of Soviet nuclear deterrence. Project 667 BDRM, known to NATO as the Delta IV class, represented the final and most refined evolution of the Soviet Union's long-running Delta series of ballistic missile submarines. Development began in the mid-1970s as the Soviet Navy sought to improve the survivability, quieting, and strike capability of its sea-based nuclear forces in response to increasingly effective NATO anti-submarine warfare. Design responsibility was assigned to the Rubin Central Design Bureau, with construction carried out at the Sevmash shipyard in Severodvinsk. The lead boat, K-51 Verkhoturye, was laid down in 1981 and entered operational service in 1985. Unlike earlier Delta variants, Project 667 BDRM placed a strong emphasis on acoustic stealth and system reliability rather than sheer missile count. The hull design incorporated improved hydrodynamics, vibration isolation, and advanced sound damping materials to reduce noise levels. These submarines were powered by 2 VM-4 pressurized water nuclear reactors driving steam turbines, providing sustained submerged endurance and patrol capability under Arctic ice. Although smaller than the Typhoon class, Delta IV boats were significantly quieter and easier to maintain. The primary armament consisted of 16 R-29RM submarine-launched ballistic missiles, designated SSN-23 Skiff by NATO. This missile represented a major technological step forward, offering improved accuracy, extended range, and multiple independently targetable re-entry vehicles. Later, upgrades introduced the R-29RMU Sineva and subsequently the R-29RMU two-laner, extending service life and combat effectiveness well beyond original design expectations. Each submarine also carried standard torpedoes for self-defense, though their strategic mission remained paramount. Project 667 BDRM submarines were optimized for bastion operations, particularly in the Barents Sea and Arctic regions protected by Soviet naval and air forces. From these patrol areas, their missiles could reach targets across the continental United States without leaving protected waters. This operational doctrine reduced exposure to NATO hunter-killer submarines and made Delta IV a stable component of second strike capability. A total of 7 Delta IV submarines were built between 1981 to 1992, entering service during the final decade of the Cold War. Following the collapse of the Soviet Union in 1991, these submarines transitioned into Russian Navy service. While many older classes were retired, Delta IV boats received the life extension programs and modernized electronics, allowing them to remain operational well into the 21st century. Although less visually imposing than the Typhoon class, Project 667 BDRM arguably proved more strategically successful. Their longevity, reliability, and adaptability ensured continuity of Russia's sea-based nuclear deterrent during periods of political and economic instability. The Delta IV class stands as a reminder that true strategic power often lies not in size, but in silence, persistence, and survivability. The Sea Shadow, IX-529, America's full-scale stealth ship nobody was meant to see. The Sea Shadow, IX-529 was a secretive U.S. Navy experimental vessel built to test stealth technologies at sea during the final phase of the Cold War. Its origins lay in the early 1980s when advances in radar-guided weapons forced naval planners to consider how surface ships could reduce detectability in the same way aircraft had begun to do. The project was developed under the Navy's Advanced Research Projects, with major contributions from Lockheed's Skunk Works, drawing directly on experience gained from the F-117 stealth aircraft program. Construction of Sea Shadow began in 1983 at Lockheed facilities, with final assembly conducted under strict secrecy. To conceal its existence, the ship was built inside a large floating dry dock, which allowed it to be moved without being easily observed. The vessel was launched in 1984 and designated IX-529, indicating an unclassified experimental ship. For years, it operated almost entirely at night off the coast of California, avoiding detection and public awareness. Sea Shadow's design was unlike any conventional warship. It used a small waterplane area, twin hull, or SWATH configuration, with two submerged pontoons connected to the main hull by narrow struts. This provided exceptional stability while minimizing radar returns from the waterline. Above the surface, the ship featured sharply angled, faceted surfaces designed to scatter radar energy rather than reflect it back to sensors. Every visible element, from the superstructure to the exhaust arrangement, was shaped with radar cross-section reduction in mind. The ship was diesel-powered and relatively small, measuring approximately 50 meters in length. With a displacement of around 560 tons, it was never intended to carry weapons or operate as a combat vessel. Instead, its mission was to serve as a full-scale test bed for radar, infrared, acoustic, and visual signature reduction. Trials focused on how stealth shaping performed in real maritime environments, including rough seas, salt corrosion, and variable radar angles. Sea Shadow remained classified for many years, fueling speculation and rumors when occasional sightings occurred. It was finally revealed to the public in 1993, after the end of the Cold War reduced the need for extreme secrecy. By that point, its primary mission had already been accomplished. Data gathered from Sea Shadow influenced later surface combatant designs, particularly in shaping and signature management, even if no ship ever replicated its exact form. The vessel was decommissioned in 2012 after decades of intermittent testing and storage. Unlike most naval ships, it had no direct successor and no combat record. Its importance lay in what it proved, rather than what it did. Sea Shadow demonstrated that stealth principles could be applied to surface ships at full scale, reshaping naval design philosophy. It was never meant to be seen, and its success was measured by how effectively it disappeared from radar, history, and public awareness alike. Project Pluto, the nuclear-powered missile too dangerous to deploy. Project Pluto was one of the most extreme weapons concepts ever seriously pursued by the United States, a nuclear-powered cruise missile designed to fly at low altitude for intercontinental distances while carrying multiple nuclear warheads. The program began in 1957 during the height of the Cold War, driven by fears that Soviet air defenses would soon make conventional bombers and ballistic missiles vulnerable. Responsibility for the project was assigned to the Lawrence Radiation Laboratory in Livermore, California, under the direction of physicist Edward Teller, with major engineering support from the Air Force and the Atomic Energy Commission. At the heart of Project Pluto was the Supersonic Low-Altitude Missile, or SLAM. Unlike conventional missiles, SLAM would use a nuclear ramjet engine, designated TORI, which relied on an unshielded nuclear reactor to heat incoming air and generate thrust. This eliminated the need for fuel and allowed the missile to theoretically remain airborne for days. Operating at speeds above Mach 3 and altitudes as low as a few hundred meters, SLAM was designed to evade radar and terrain mask its approach while releasing nuclear warheads over enemy territory. The nuclear reactor itself was the most radical element. Air flowed directly through the reactor core, which was composed of hundreds of thousands of ceramic fuel elements operating at extreme temperatures. The exhaust was intensely radioactive, meaning the missile would contaminate everything it flew over even before detonating its weapons. From a strategic perspective, this was considered acceptable at the time, as the missile was intended only for total war scenarios. Ground testing of the reactor took place at the Nevada test site beginning in 1961. To support these tests, a massive facility known as Jackass Flats was constructed, including a rail system to move the reactor remotely due to radiation hazards. The Tory III-IA reactor achieved initial criticality in 1961, followed by the more advanced Tory YIC, which successfully operated at full power in 1964. These tests demonstrated that the nuclear ramjet was technically feasible. Despite these successes, Project Pluto faced growing problems. Guidance accuracy at low altitude remained questionable, launch methods were complex, and the missile's indiscriminate radioactive effects raised ethical and political concerns. More importantly, rapid advances in intercontinental ballistic missiles made Pluto strategically redundant. ICBMs were faster, cleaner in deployment, and far more practical. In 1964, Project Pluto was officially canceled before any flight tests occurred. The missile was never built beyond test hardware, but its legacy remains unsettling. Project Pluto demonstrated that nuclear propulsion could be weaponized in unprecedented ways, and it stands as a stark example of Cold War thinking pushed to its most destructive logical extreme. The Dead Hand Infrastructure, the automated system built to launch the end of the world. The system, known in the West as Dead Hand, officially designated Perimeter, was one of the most secretive and unsettling elements of Soviet nuclear command and control. It was developed during the late Cold War to ensure a guaranteed retaliatory nuclear strike, even if the Soviet leadership and primary command structures were destroyed in a first attack. Work on the system began in the early 1970s, driven by fears that a surprise decapitation strike by the United States could paralyze Soviet decision-making and neutralize its nuclear deterrent. Responsibility for Perimeter was distributed across multiple Soviet institutions, including the General Staff, the Strategic Rocket Forces, and specialized design bureaus involved in command and control systems. The system became operational around 1985, during a period of heightened tension marked by NATO exercises such as Able Archer 83 and growing concern over miscalculation. Its existence was kept strictly classified, and even many senior officers were reportedly unaware of its full capabilities. Perimeter was not a single machine, but a layered infrastructure combining sensors, communication networks, and command logic. It continuously monitored indicators of a nuclear attack, including seismic shocks from detonations, radiation levels, atmospheric pressure changes, and disruptions to military communications. Crucially, it also assessed whether normal command authority was still functioning. If the system detected evidence of a massive nuclear strike and confirmed the absence of human command intervention, it could be activated to initiate retaliation. At the core of Perimeter was a set of specially modified command missiles. Instead of carrying nuclear warheads, these missiles carried powerful radio transmitters. Once launched, they would fly over Soviet territory and broadcast authenticated launch orders to surviving intercontinental ballistic missiles, submarine forces, and bomber units. This ensured that even isolated or damaged launch crews could receive the final command to fire. Contrary to popular myths, Perimeter was not fully autonomous in normal conditions. Activation required prior authorization during periods of crisis, effectively placing the system on standby rather than leaving it permanently armed. This design reflected an attempt to balance deterrence with control, though critics argued that any automated launch mechanism increased the risk of accidental nuclear war. Following the collapse of the Soviet Union in 1991, Perimeter's status became the subject of speculation. Russian officials later confirmed that a modernized version of the system remained in existence, emphasizing its role as a stabilizing deterrent rather than a doomsday device. Statements in the late 1990s and 2000s suggested that the infrastructure had been updated to integrate with contemporary command systems. The Dead Hand infrastructure was built around a grim logic. that the certainty of retaliation would prevent an attack in the first place. It embodied the most extreme expression of mutually assured destruction, transforming the fear of annihilation into an automated guarantee. Even by Cold War standards, it represented a sobering acknowledgement of how close human survival rested on machines designed for the unthinkable.